Okay, so a very good morning. Welcome to the third and final day of the STEMS camp. Thank you very much for attending, and we hope all of you are having a great time. Flagging off today's proceedings, I'm honored to introduce Dr. Rajiv Gandhi from the Rutgers University. He obtained his MSc in Computer Science from the Virginia Polytech Institute and State University, and his PhD from the prestigious University of Maryland. His research interests include theoretical computer science, specifically in approximation and randomized algorithms, and the much of theory behind algorithms and complexity. He is very well recognized for his immense passion for teaching and has won numerous accolades for the same, including the Warren I. Sussman Award for Teaching Excellence at the Rutgers University in 2014. Since 2009, he's also been working with high school students as a part of the program in algorithmic and combinatorial thinking. Uh, Today, Dr. Gandhi will take us through this wonder called algorithm design, in which we shall talk about the very well known problem, stable magics. So, without any further ado, over to you, Dr. Gandhi.
Thank you very much, Aniruddha. Thank you for inviting me, and it's a pleasure to be here. So let's dive straight into the problem. So I'm going to talk about the stable matching problem. And the input is um, let us say that there are n. Let us say that there are n men and n women, and each person has a preference list ranking each person of the other gender. Um, and let's just let me make it clear that there are no ties, and you will see what I'm trying to say here. And our objective is to find a stable matching. So let's understand the problem first, right? So what is a stable matching? So first, let's understand what is a matching, right? What is a matching? Matching is a term that comes from graph theory. All in this case, all we want is here the condition. All this is saying is we want to pair each man with exactly one woman. Yeah. So let's take an example. Suppose we have. Let me just illustrate, draw a picture, and it will be more clear. So let's say that we have men M1, M2, M3, Mn, and let's say we have n women W1, W2, W3, and Wn. Yeah. And M1 has a preference list which says W5, then W19, and so on, right? The ranking all the women. That is, M1 says I prefer to be with W5, then W19, and so on. Similarly, M2 says I want to be with W8, and then so on. And similarly, M3 and so on. Similarly, W1 says I want to be with M1, then M8, then M5, then M84, and so on. Yeah. And there are no ties. That is, they have to rank every person of the opposite of the opposite gender, and they have to put it. And there can be no ties. So a woman cannot say I like these two men equally or something. Yeah. And the objective is to pair each man with exactly one woman. How do we do that? Meera Bhardwaj, how will we do that? You can unmute yourself and talk.
So there's Pranav Chaudhary with his raised hand. Maybe do you want to give a go?
Yeah.
I'm sorry,
So,
what did you say? Yeah. Okay, Pranav, go ahead.
so we can number these preference order like for M1, W5 can be labeled as 1, W19 as 2, and then the total sum after pairing should be minimum. We can do like this.
Okay. All right. Anyone else? Okay.
So
Arnab
we can,
Chavan. Yeah, go ahead. Tanuj, yeah.
so we can construct like two different matrices for men and one for women, and
Two different matrices.
yes, sir. And we
Okay.
can assign weightages to each of them, like
Okay.
one for their according to their preference. Say for women, one M1 has the highest preference, and we will be allocating that amount of that amount of value to it, and then maybe we
Okay.
can calculate a matrix product, and perhaps like that.
Okay. 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 Sarthak Malik. Any ideas?
We can probably start to pair them. If they become unstable, we can iterate through and
What do you mean by unstable? I don't know. What do you mean by unstable?
I mean no one gets the uh, it- it's not the most preferred matching.
Okay. Look at what I'm asking. I want to pair each man with exactly one woman. Anand Lunia.
So are there no other conditions for now? We just want to pair one man with one woman.
The question is what I've written. This is a question in your exam. You have 30 seconds left. Your life depends on it. What will you do?
If there are no other conditions, we can just pair any man with any woman. It won't matter.
Exactly, right? I mean, why are we complicating the problem? As Anand said, look, he wants us to pair a man with exactly one woman. I will do that. I will pair M1 with W1, M2 with W2, M3 with W3. Life is good. We can go home, right? So look at problem what is asked for. Why are we, and people are defining instability. I've not even defined that, right? So I've just said this is what I want. That's what Anand is saying, and this is what we can do. In that case, my lecture will be over and we'll go home. But I need to fill in 1 hour. That's what I was told. So let's make the problem a bit more interesting. So as Anand said, that look, this seems to be a bit weird because you may use big words, stable matching, but you have not defined what stability is. And somebody else also talked about instability. So let's talk about what that means. So want to pair each man with exactly one woman. The condition is such that no two people prefer each other over their existing partners. Yeah. So let's understand it. So what this is saying is that suppose M2 is paired with W2, but suppose that M2 prefers W3 and W3 prefers M2 over their current partners. That is, M2 prefers to be with W3 more than to being with W2. and W3 prefers M2 more than W3, then nothing stops them from eloping, right? So that is instability. So this is instability. This is an instability if and only if M2 prefers W3 over W2 and W2 prefers M3 over M2. Yeah. Keep in mind, both people have to prefer each other over their existing partner. Yeah. Yeah. Only then there is an instability. Yeah. Any questions about the problem? So what we want is we want a pairing of the n men with the n women such that there is no instability. Any questions about any of this? Yeah,
I
Shaurya, go
have a
ahead.
question. What I understood is that here M2 prefers W3 over W2 and W3 prefers M2 over M3.
Oh, did I? Oh, sorry. Oh, sorry. Yeah, I didn't write that correctly. Okay, M2 prefers W3 over W2 and W3. Sorry. Yep, you are correct. I have made a mistake here. Okay, W3 prefers M2 over M3. Good. Thank you. Thank you. Yeah. Thank you, Shaurya. So is this clear, everyone? Okay. So we want to pair the n men with the n women such that there is no instability. Okay. All right. So the first question is that okay. So given okay. So let us just So an important question is do all instances or do all inputs have a stable matching? Right? Rishit Chaudhary, is the answer yes or no? That is no matter what the preferences are. Can we always guarantee there is a stable matching, or for some inputs there could be no stable matching? Ishan Jafar. Okay, Rishit is saying yes for all instances. Okay. Sombit Bose.
Sir, I think it may be possible that it does not happen, because if I take a particular case where you rank all the men and women and a particular man has choice of, suppose I am picking M8 and he has choices of W1, W2 and W3, which are already preoccupied by the previous men. So it is not quite possible in that case.
Yeah, but you're talking of algorithmic. We are talking of input instances. Without okay. So let's see. I don't know the answer right now. Let's figure it out as we go along. Okay. So now let's at least say that suppose somebody also tells us that an instance has a stable matching. In that case, can we find a stable matching? Yeah. So let us say that So let us say that some men are already paired with some women, and let's say that this is so we are paired, but it's not like a done deal, let's say, right? So let's say that the pairing is this way. So this is M1, M2, M3, W1, W2, W3. Suppose this is the pairing, and of course there are other men here and other women here, and let's say this is M4, this is M5, and so on. Now, what should M4 do? What should M4 do? M4, okay, let's say that M4 is going to propose to some woman. Which woman should M4 propose to?
So suppose
Bhamidi. Yeah, okay, Somit, go ahead.
Yeah, so the example of which I was telling that suppose M4 is now proposing to W3, but
no, there is no suppose proposing to. I am asking whom should M4 propose to?
Oh, ideally W4.
Ideally W4. Why?
He'll propose to the woman highest on his list.
Propose to the woman highest on his list, right? Quite naturally, right? Quite naturally. So M4, and let's say that the woman highest on his list is, let's say, W4. Suppose. Then life is good. W4 is free. M4 and W4 get engaged. But suppose the woman that is highest on his list is, let's say, W2. So M4 proposes to W2. What should W2 do? Parth Agrawal. What should W2 do? Bhamidi.
Sir, since it's a stable matching, so W2 should reject.
W2 should?
Reject the proposal of M4.
Why should W2 reject? Why? Bhamidi, go ahead. You want to say something?
No, look at the ordering of M4 and look at the highest after W1, W2, W3 in his ordering and then associate.
I'm sorry, could you repeat that?
Yeah. Look at the ordering of M4. Among those, see the highest after these three and associate.
I see. Okay. So we have various options. So anyone else?
W2 looks at their own list, and if M4 is higher than M2, then go for M4. Otherwise, stick to M2.
Exactly. Very simple, right? What Rohan is saying is that, look, W2 has a choice. I mean, W2 can do whatever W2 wants. W2 says, look, ask the question, do I prefer M4 over M2 or do I prefer M2 over M4? If W2 prefers M2 over M4, then it is status quo. If W2 prefers M4 over M2, then W2 decides to be with M4 and M2 becomes free, right? It's quite natural, and that's what Rohan is suggesting. So let's write an algorithm based on that. So algorithm, so this was the key idea. So initially, all men and women are free, and second is while there is a free man M who has not yet proposed to every woman, do let W be the highest ranked woman on M's list whom M has not yet proposed to. Yeah, highest ranked woman on M's list whom M has not yet proposed to. Step 4, if W is free, this is the case we discussed, then MW becomes engaged, becomes a pair. Else, if W prefers, okay, sorry, if M prime W exists, then if W prefers M to M prime, then MW becomes a pair, and 9 M prime becomes free. And at the end, if the while loop ends, we will return. If the while loop ends, we will return all engaged pairs. Yeah, that's the algorithm. So first thing I just wanted to check, any questions about the algorithm? Does everyone understand what the algorithm is saying? Right, wrong, correct, not correct? Let's worry about that later. Any questions about
It's
anything?
clear.
So what is the M dash?
M dash is, okay, so M dash is another man. So there is a pairing, so when M proposes to W, so it's like, okay, M dash or M prime, what I call M prime, is M2 in this case, because when M4 proposes to W2, W2 is currently engaged with M2. So your M prime here is M2. Is that clear?
Yes, sir.
Okay. Good. Okay. Right. So let's first even ask, does this algorithm even terminate?
Yes, sir.
Sorry, it will terminate, Rohan?
Yes.
How do you know that?
Okay, so let's say that like if a woman is unpaired, her value is 0. If she's paired to the last man in her list 1, and so on till n.
Yeah, but what does all that have to do with the algorithm terminating?
Every step of the algorithm, the value increases. The sum of the value increases.
Okay.
So, and it cannot be an infinitely increasing sequence because n square is the maximum achievable. So it has to terminate at some point.
Okay. Yes, but it can stay the same, no?
No, sir. Because like if a man asks a woman to proposes, and he can say the woman rejects. He goes through all his list. Some woman must accept.
Okay. Good.
So the
Very
value
good. Right?
increases.
Very good. So what Rohan's argument is, so first lemma is that the algorithm, so by the way, this algorithm is due to Gale and Shapley. The algorithm terminates. Yeah. And the argument that was given, idea or the why, okay, let me not say why. Let me say proof sketch, is that each man makes at most n proposals, right? And at most n men, therefore at most n squared proposals. So in at most n squared iterations of the while loop, the algorithm must terminate. Thus, in at most n squared iterations of the while loop, the algorithm terminates. Yeah. So the key here is that a man does not propose to a woman more than once. Yeah. So it says whom M has not yet proposed to. That is important, right? Okay. Second observation, we can do, yeah. Okay, let me just make it a lemma. How many times can a woman get engaged, then become free, then get engaged, then become free, then get engaged, then become free?
Never.
I'm sorry?
You can just become engaged, but if a woman is engaged, she cannot become free.
Correct. Very good. Right. So what Rohan is saying is that once a woman becomes engaged, once a woman receives her first proposal, she remains engaged. She always remains engaged, and her partners can only get dash over the course over the course of the algorithm. Someone else, Anant, fill in the blanks.
Higher on her list.
That's right. Right, can get better. Right, over the course of the algorithm. Right, that's right. That is, her partners on her list will only get will be of a higher preference. Right. Okay. Now what we want to show is the first thing we want to show is that at the end of the algorithm, at the end of the GS algorithm, every man is engaged to exactly one woman. Again, proof sketch. Suppose a man M is free at the end of the algorithm. Yeah, suppose the man is free. Why did the algorithm end? Okay, let me write it this way. We know that the algorithm has ended, which means that M must have what? M must have someone
Proposed to all the women in his list.
Excellent, excellent, right? Must have proposed to all women, all women. Okay, let me be even more precise. Propose to each of the n women. Yeah. So what would be the status of the all of the n women? From the previous lemma, we can say that this means that all women are engaged, but this further means that at most n minus 1 men are paired with n women, implying that some man must be paired with at least 2 women, which is not possible. Which is not possible because our algorithm makes sure that is not possible, right? If a man is engaged to a woman, he is not going to go and propose to another woman, right? It's only the free men who propose to the women. Yeah. Okay, good. Right. So similarly, you can, so this is the proof idea. The next theorem is that the GS algorithm or the Gale-Shapley algorithm yields a stable matching. That is, we want to show that at the end of the algorithm, we now know that all the n men are paired with the n women. We just want to prove that there is no instability. Proof. Assume for contradiction that the output of the algorithm has an instability. Yeah. So let's say that in our algorithm, M is paired with W, M prime is paired with W prime, but M and W prime prefer each other over their existing partners. So this is the instability. Right? So we know that the preference list of M must be, the preference list of M must be W prime and then W. Has to be that way. The preference list of W prime has to be M and then M prime. Yeah. Because they prefer each other over their existing partner. Can somebody come up with a contradiction now? Yes, Shaurya, go ahead.
We can say that M must have proposed to W prime before W.
Okay, 1 second. Why is Shaurya saying that M must have proposed to W prime before proposing to W? Can somebody tell me why Shaurya is making that claim? How does he know all these things?
Sir, because W prime is before W in his preference list.
Excellent, 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 right? Because W prime is higher ranked on M's list than W. Shaurya continues. So just one second. What Shaurya is, he's saying some good things. Let's write it down. So he's saying that M must have proposed to W prime before proposing to W. Good. Shaurya, continue.
So, and here W prime must have rejected M.
Okay, one second. W prime must have rejected M, right? Why? Because M eventually ends up with some woman who is not W prime. So it must be that M got rejected, right? By W prime. Continue, Shaurya.
Then, since W prime has rejected M, it means W prime was with someone whom she preferred more than M.
Okay, very good. So this means thus W prime is with someone who she prefers more than M. More than M, yes. Continue, Shaurya.
But in the end, we see that she ends up with M prime, whom she prefers less than M, and
okay,
our algorithm
very
does
good.
not allow this.
Very good. Since W prime's since a woman's partners keep getting better, it must be that it must be what? It must be that M prime is ranked higher than M on W prime's list. A contradiction, right? What is it contradicting? It is contradicting that M is ranked higher than M prime. Yeah, good, very well explained, Shaurya. Okay, so this shows that the GS algorithm outputs a stable matching. Our assumption was that if the algorithm had a stable matching, then GS algorithm outputs it. That's great. Now, under what condition can the algorithm not have a stable matching? Not the algorithm. Under what inputs can there be no stable matching? Someone.
So the proof idea never used that we are assuming there's a stable matching.
Amazing, right? So what Rohan is saying, look, nowhere in the proof have we assumed that there is a stable matching. What does that mean? That means that every input must have a stable matching, right? This is what some of you said, some of you felt no. I mean, when I first saw the problem, I felt no, the answer that cannot be true, right? But indeed, this shows that every input has a stable matching. Yeah, excellent, excellent. So we have a few minutes left. Let's go over some properties now. The one question to ask is, let's look at this algorithm. It doesn't tell us, if you see this, it doesn't tell us. So the question is, which man, okay, let me not say this way. Let me say, what ordering of the men? That is, in which order should the men go and propose? Right? I mean, if I am free, somebody else is free, should I go first? And let's say that I am free, X is free, we both like the same woman. Is it should I go first? Does that help me? Or should the other person go first? Or what should be done? Pranav, go ahead.
So it doesn't matter which goes first, because it would depend on the woman's preference list and it will remain the same. So anyone can go first.
So you are telling me that no matter who goes first, it doesn't. There will be only one partner for W.
Yes, sir.
Okay.
At the end.
Okay, this is all very good, because this is not what I thought when I first saw this problem. I thought that, well, no, I mean, I should go first if I like a woman, because that would help me be with the woman, right? So okay, so let's see what Pranav is saying. Pranav is saying, so now some definitions again. We say valid of M, that is, who are the valid partners of M? They are all the women W, all the women, okay, all the women, such that there is a stable matching containing MW as a pair, right? That is there, all the women with whom M can be paired up in some stable matching, right? God may know many stable matching, some stable matching, then we say that W is a valid partner of M. The best valid partner, if and only if W belongs to the valid partners of M, and second condition is for all W prime ranked higher than W on M's list, W prime is not a valid partner of M. Yeah, W prime is not a valid partner of M. What is it saying? What are we saying with respect to best of M? We are saying the following. We are saying that suppose you have a man M, and you look at its preference list, and let's say W is here and this. It is saying that all these women who are ranked higher than W on M's list, they are not valid partners. That is, W is the highest ranked woman who is a valid partner of M. That is when we say W is the best valid partner of M. Yeah. What is surprising is that, what is surprising theorem, at least to me when I first seen it, is saying that Gale-Shapley algorithm, okay, in all executions of the GS algorithm, the output is S star, where S star is pairing of M and W, where W belongs to valid, okay, sorry, W is equal to best of M. Yeah, this is the theorem that we are going to prove, or we are going to quickly give a sketch. Yeah. So we are saying that assume for contradiction that in some execution E of the GS algorithm some men get rejected by their best valid partners, right? Among these men, let M be the first man to be rejected by best of M, which is who is W, right? W is the best of M, and W. So algorithm is coming along fine. There are rejections going on, but none of those rejections are by valid partners. So nobody complains. Suddenly M complains. M says, "Oh, I just got rejected by my valid partner," and because W is the first valid partner on M says it has to be the best valid partner. M is complaining about that. Okay. So let's ask what happened. Why did W reject M? W rejected M because of some man M prime. But because W is a valid partner of M, there must be some stable matching. By definition, there must be a stable matching S star such that the following scenario is there, right? So S star, in S star, M is paired with W because W is the best valid partner of M. That's why it's a valid partner of M. W is a valid partner of M, and so there must be, by definition, some stable matching that contains MW as a pair. Okay, so let me such that MW is a pair in S star. Yeah, so S star looks like this. Well, whom is M prime paired with? Well, some woman W prime. What are the preference lists of, can we say anything about the preferences? Well, we know one thing, that M prime must come before M. Why? Well, because W rejected M because of M prime. So M prime must come higher. But because S star is a stable matching, M prime cannot prefer W over W prime. So it has to be W prime and then W. Right? Because if it was W and W prime, then M prime and W could elope. Right? They could run away. And so that cannot be the case. And S star is a stable matching, so that cannot be the case. Now, I want somebody to finish the proof. I'm just going to get just set up something. This is the timeline. This is timeline. This is the point where M is rejected by W. M is rejected by W. Rohan, go ahead. Yeah, Pranav, go ahead. Yeah, sorry, who's talking? Rohan. Yeah, go ahead. Yeah.
Yeah, so assuming that W prime comes before W, M prime must have proposed to W prime, but when M prime is now with W, so that means W prime rejected M prime at some point before M is rejected by W. So this cannot happen because we assumed it's the first point this has happened.
Fantastic. Very well explained. I couldn't have said any better. What Rohan is saying is that, look, M was rejected by W because M prime is available to W. But that means what Rohan is saying is that M prime must have, because M prime in the GS algorithm proposing the decreasing order of preference list, M prime must have proposed to W prime before this point and must have got rejected. M prime gets rejected by W prime. We know that W prime is a valid partner of M prime. Why? Because, because in S star, M prime and W prime is a pair, right? And thus, W prime belonging to valid of M prime. Let me write that so it's very clear. Therefore, M is not the first person to be rejected by his best valid partner, right? There is somebody else, but it's definitely not M, right? Because this rejection with a valid partner happens before that, as Rohan said, and hence this is a contradiction, right? A contradiction. Any questions about this proof? Feel free to ask. You can unmute yourself and ask. Okay, I just want to end by saying just two more things. First, I want to say another lemma. GS algorithm, the way we have written, where men propose and women dispose, is the women, it doesn't favor the women. Each woman ends up with her worst valid partner. What does worst valid partner mean? It means that, what does worst valid partner mean? It means that if you have woman W and this is the man who's, we are saying that the lowest ranked valid man is the worst valid partner of W. Yeah, sorry, I'm going a little fast here. So I'm saying that who are valid partners of W? All the men such that W can be paired with M in some stable match. Who is the lowest ranked valid man? Who is the worst valid partner? Is the lowest ranked M who's also who is in the valid of W. That's it. What we say is that if the men propose, then every woman ends up with their worst valid partner. I will not do the proof of this. If you use the previous theorem, then it just becomes a 4-line proof. It's not hard. I would leave it for you to do it. Yeah. So GS algorithm, the way it's written, favors the men. If we want it to favor the women, we should have the women propose. Yeah. Now, then what happened is, so this is a GS algorithm, right? This was the algorithm that they came up first, and then I had an amazing idea, and I went ahead and improved this algorithm. It's a very short algorithm. My algorithm is very short. So I will say Rajiv's algorithm. Rajiv's algorithm is very short and sweet. It says try all permutations of women for each permutation pi of women, pair man mi with the ith woman in the permutation. Just pair them. After you do that, check. Okay, after you do that, check for instability. if unstable, if unstable pair exists, then a repeat. Repeat meaning try another permutation. Sorry, I have not written it very well. I'm saying try another permutation. Just keep doing that, right? Just a very short algorithm, right? So you see that this algorithm is so much simpler and so much preferable, because you can just write this in very short than the GS algorithm. Shaurya.
I had a question. Here, from what I understand, is there will be only one valid partner for a woman and only one valid partner for a man. Like there's only one stable matching that exists.
Not necessary, but anyway, I need only one stable matching. Whether one exists or 500 exists, it doesn't matter. I'm just trying all permutations of the women. So I hope my algorithm is clear. So Shaurya, what I'm saying is, all the men, they will line up and stand, right? They will not move. I try one permutation of the women opposite the men. Whichever woman comes in front of the man, they will get paired up. Then I ask, hey, is there any instability? And if there is an instability, I tell the men, don't move. I line up another ordering of the women. I do the same thing. I check for instability. If there is instability, I try the third ordering of the women. And I keep doing that until I find a stable matching, which I know exists. Shaurya, is that clear?
Yeah, but I think there's only one possible stable matching.
Yeah, fine. All we want is one stable matching. Why are we worried about? First of all, that is not true. An input can have many stable matchings. But I just want one stable matching, and it'll output that.
Okay.
Is something about my algorithm not clear, Shaurya?
The algorithm is clear, but like when you said above in that lemma that a woman will always be paired with the lowest ranked valid man in her.
No. 1 second. Shaurya, that is over. Gale-Shapley algorithm is over. This is the end of the Gale-Shapley algorithm. Then I'm just telling you my algorithm, which is an amazing short algorithm, which clearly is much better than the Gale-Shapley algorithm. I just wanted to quickly tell you that and leave it at that.
Okay, so you mean the GS algorithm will give you a stable matching, but it will give you one stable matching, and if there exists other stable matching, you can get it from Rajiv's algorithm.
Okay, that is so. Okay. So GS algorithm, the way it's written, that is men proposing, women disposing, will give you exactly one stable matching. Correct? You agree with that?
Yeah.
Okay. GS algorithm can also give you another stable matching if you make the women propose and the men dispose. Do you agree with that?
Yeah, correct.
Okay. I am now saying that's the end of GS algorithm. I'm saying now listen to Rajiv's algorithm, which is an amazing algorithm. And what I'm saying is try all permutations of the women and just pair up every man with the woman who comes in front of him, and check for instability. If there is instability, try another permutation of the women. Continue that way until you get a stable matching, and we are done. That's all. I'm just saying it. Do you agree with that?
Yeah, this is okay, but how is this a wonderful algorithm? I mean, GS is much.
No. 1 second. Shaurya. Let's count. I'm assuming you know how to count. This is line 1, line 2, line 3. 3 lines and we are done.
No, but this is.
But the execution will take more time.
1 second. Let me talk to Shaurya. Yeah, Shaurya, go ahead.
But the execution will take much more time.
How can it take much more time?
Maximum
it's a 3-line algorithm. How can it take much more time?
There we had a maximum of n square steps, and here we have a maximum of n factorial steps. And for sufficiently large, n factorial will be larger than n square.
Very good. Right. So this, what Shaurya is saying, is a terrible algorithm. Right? Terrible algorithm. something that will choke your computer, right? If when n becomes very large, because Shaurya is saying all permutations of the women is n factorial. Bad, right? All the point of the point of saying this was that a brute force approach, which is what Rajiv's algorithm says, tries n factorial permutation. It takes n factorial steps. By clever insight, we could bring it down to n squared. And that is what the beauty of algorithm design is. That is, how do you efficiently solve a problem? I will end my talk there. That's all I want to say, that there are lots of problems for which some clever insights can drive down the execution time tremendously. I'll stop here and take any questions that people may have.
Sir, I had a doubt. Sir.
Yeah.
So like, what if like the number of stable matchings, like what if we get to know that the number of stable matching is a constant, like if you take the number of stable matchings divided by number of all matchings, if it turns out that the ratio is not 0, like if it is tending to some value between 0 and 1, then sir, this Rajiv's algorithm on average, it will have like quite better odds than of n factorial. So sir, if we, before saying of n factorial, don't we have to prove that that ratio tends to 0 as n tends to infinity?
What do you mean by ratio tends to? If you're saying ratio, I mean, what? So we know that every input has has at least one stable matching, right?
So sir, I'm saying the number of stable matchings. If that number of stable matchings divided by number of all matchings, if that ratio tends to some value, some non-zero value, as n tends to infinity, so then by probability we can say that that most probably it will not go for n factorial iterations. It will stop somewhere before, because we know that the probability of not reaching is 1 minus that ratio, and so by more on average we'll see that it will not run for n factorial. It will run for pretty like for some small value. So Rajiv's algorithm will turn out to be pretty good if that ratio tends to some constant.
So there are two things, Rishvik, here. First of all, we are doing a worst case analysis. So in the worst case, what will happen? Second thing, even if we take average case, right? I mean, so that is, why do you think that very quickly some permutation will give us a stable matching? I mean, if you talk about all the matchings, there are n factorial matchings, right?
I'm saying that we have not taken anywhere what is the number of stable matchings. We have not shown how many stable matchings exist. I am saying that if the number of stable matching is some constant ratio multiplied by n factorial, then we can say Rajiv's algorithm on average will perform pretty good. So before.
Oh, I see. What you are saying is that if there are lots of stable matchings, then you are saying that the chances of our algorithm performing well is quite high.
Yes, sir.
Yeah, but that is not necessary, right? I mean, it's not necessary that that there are that many stable matching. There are inputs on which there is exactly one stable match. Then it's like needle in a haystack, right?
Yes.
Yeah, Pranav, go ahead.
Sir, in the third point of Rajiv's algorithm, how do we check for the instability? Means
again, it's. I mean, you can check. You can do brute force. You can check every pair. You can check every pair of that is every man with every woman and ask, hey, do you form an unstable pair? I mean, don't think too much, because this algorithm, even if step 3 is done for free, what Shaurya and you all said is that this is just a terrible algorithm right in the first step. If we are going to try all permutations, forget if all other steps were free. Still, trying all permutations will be very bad. But yeah, if you want to check for instability, we can just take every pair, man, woman, and ask, are you stable? Are you unstable?
Okay, sir.
Okay.
Maybe if we improved Rajiv's algorithm to a point where, like, when from a certain permutation of women, we take all the unstable pairs and we learn from that to make better permutations instead of just trying randomly all permutations.
That's a good point. That's a good point, right? What Shaurya is saying is that, look, why are you throwing away everything? Okay, you made a mistake. Don't throw away everything. Learn from that and maybe be a bit more clever when you come up with the next permutation. Totally. Yeah. I mean, yeah. Very, very valid points. Yeah.
Is there a better algorithm than O of n square?
I don't know. I don't think so. I mean, because Gale-Shapley algorithm is used, seems to be used in practice, I think. So probably not.
Is it provably the best?
I'm not sure. I don't think. Yeah, I mean, I don't think there is anything better than n squared. But I don't think that it has been proved that nothing better than n squared exists. But I've not kept up with the literature in this on this problem, so I don't know all the what the latest results are. But I don't think that it'll. I don't think there is any theorem that says nobody can do better than n squared.
Okay, thank you, sir.
Okay.
So what are some nice generalizations of this stable matching problem, if any? If any.
There are, so again, I'm not kept up with the literature, but I know that my colleague Ricky Vora at Penn, he has worked on, I think, problems like what if, so this is used a lot when let's say that people are looking for jobs, right? And let's say that there is a couple who wants to be at the same university, right? And let's say that university has let's say 3 positions open. Then, I mean, is it possible? And so on one side there are different people who want to go to a particular university. I don't exactly remember the generalization that he worked on, but it has something to do with that if the universities have capacity. So here it's like every vertex has capacity exactly 1, right? But suppose universities had more capacities, that is, say the vertices on the left had more capacity. Can we? I forget exactly, but I think it was I think it was like, how do you satisfy? Let me think what. Yeah, I don't exactly remember, but I think the result was something to the effect that if we violate the capacity by a little bit, then we can make everyone happy. Now, what making everyone happy means, I don't totally remember right now. But I think there are if you want to know more about the literature on this, I think Kavita Telikapalli at TIFR has done some work on this, and also Ricky Vora at Penn, and I'm sure there are others also working on it. I've just not kept up with the literature on this. Yeah.
Thank you, sir.
All right. Thank you, Anirudh. And thank you all for inviting me. You all are a very impressive group. I mean, it takes me a long time to get through this, even with my undergraduate students. So, very impressive, and keep up all the good work.
Thank you very much for your words, sir.
Thank you.
Any final questions? So if not, so please do join me in thanking Professor Rajiv Gandhi for this wonderfully interactive talk. So we couldn't have asked for a better talk on Valentine's Day. So thank you very much for that. We meet at 3:30 p.m. today when Professor Shankar Bhamidi of the University of North Carolina, Chapel Hill will be giving a curiously titled talk, Networks Everywhere. So coincidentally, he is Professor B.V. Rao's son, who is here in the meeting today. So hope to see you all there, and hope you enjoyed. So thank you very much.
Thank you, sir.
Thank
you
you
for accepting our invitation.
Bye-bye.
Excuse me.
Sorry? Yeah.
Is there any such, like, a triple stable matching problem. Like you have 3 sets of people.
I know what you're saying. Again, I don't know if this has been generalized that way. I see what you're saying. It could be like men, women, and pets. I don't know. That would be interesting. I again haven't kept up with the literature, but there may be some generalizations on that front. Yeah.
Okay. Thank you.
Yeah. All right, folks. Bye.
Okay, thank you for joining and bye.
Bye, Anirudh. Thank you. Nice meeting you. Yeah.